Okay, in today's video, I'm going to go over how to use Newton's second law to calculate the acceleration of an object, and there is friction between the object and the surface, and there is a force that is applied to the object, and that force is applied at an angle above the horizon. Okay, so here's a description of the problem. We have a rightward force of 50 newtons applied 35 degrees above the horizontal to an object that has a mass of 6 kilograms. It's moving across a rough surface. The coefficient of friction is 0.12. We want to draw all the forces, label all the forces, calculate the magnitude of the forces, and then calculate the acceleration of the object. Okay, so let's get all the information out of the problem and onto the page here, onto our diagram. This, of course, is our box, and it tells us the coefficient of friction. This symbol mu, the Greek letter mu, is a symbol for the coefficient of friction. The coefficient of friction is 0.12. All right, now we're going to draw and label all the forces. The first force is gravitational force downwards. The box is not falling through the surface. It's on the surface, moving across the surface. That must be a normal force that points upwards, Fn. And we're going to have the applied force at an angle above the horizon. So here's a horizontal line. For reference, we have the applied force acts upwards. The applied force, 15 newtons. It acts at 35 degrees above the horizontal. So there's the angle. That angle is 35 degrees. And the box is moving to the right. It's across a rough surface because there is friction, coefficient of friction, and that tells us that there must be a friction force, and the friction force is opposite, opposes the motion, and we label that FF for friction. Okay? Now, when we have an applied force or a force that acts at an angle that's not in the x or the y direction, we're going to have to, most likely, break that force into its component vectors, into the components that act in the x and the y direction. So we have to do that in this case. This purple vector represents the component of the applied force that acts in the x direction, so we label it FAX. And we're going to have to find the component of the applied force that acts in the y direction. This red vector represents that. We label that FAY. Okay? Now we're going to do a bunch of calculations. This problem might seem like it's pretty straightforward, but because there's the force that's applied at an angle, it makes it a little more complicated. So we're going to calculate all the forces, and then we're going to use those forces, the appropriate forces, to calculate the acceleration. So please pay attention. Okay, the first thing I think is the easiest thing to do is to calculate the weight, the force due to gravity, because it's always going to be mg. That means it's the mass times the acceleration due to gravity, which is a mass of 6. Acceleration due to gravity, 9.8 meters per second squared, 58.6 newtons, so we just label that. Now you might be tempted to just label the normal force 58.6, which if this force was acting in the horizontal direction, okay, along the x-axis, then we could do that. But this force is not acting along that, it's acting at an angle, and therefore this component is releasing this component of the applied force is actually taking up some of the normal force. And we're going to show you how we're going to do that, but we don't know how much because we have to, of course, calculate the component, the y and the x component of the applied force. We're going to do that right now. And we have a right triangle here. We know this angle is 35. We know this side is the hypotenuse is 15 newtons long. So therefore, we can use our trig functions. We have the sine is equal to the opposite over the hypotenuse. This is the angle, this is the opposite side, this is the hypotenuse, so therefore we can put in here FAY and FA, so we can relate it to this actual problem here. We're going to solve for FAY, the sine of theta times FA, and that tells us it's the sine of 35 times 15 newtons, and therefore that is 8.6, so the component of that is FAY, which is 8.6 newtons. So we can do the same thing using the cosine, is adjacent over hypotenuse. Here's the angle again. This side is the adjacent side, and therefore we're going to put FAX. We're going to put FA again for the hypotenuse because the hypotenuse is still the applied force. Solve for FAX. Cosine of 35 times 15 is 12.29 newtons, so that is 12.29 newtons. Okay, so we need to do that before we can calculate the normal force, and really before we can calculate the force of friction, because the force of friction requires us to know the normal force. All right. So the next thing I think we're going to do is we're going to calculate the normal force. Okay, because we can't calculate the friction force yet. So let's go on and calculate the normal force. We're going to sum up. Oh yeah, we're going to get rid of. I'm going to cross this off because we found its components. So we're not really going to use this force anymore, the applied force. Not that we're getting rid of it, or not that it's gone to 0 or it's going away, but we're going to use the components instead of the actual. So I just like to cross that off so I know that. Okay, now we're going to find the normal force. In order to do that, because the normal force acts in the y direction, and we know this force, the other force in the y direction, and we know this force, the other force in the y direction. This is what we don't know, so we can use Newton's second law to sum up the forces in the y direction. They're going to equal the mass times the acceleration in the y direction. But the box is moving to the right. It's not moving or accelerating in the y direction. So therefore we know that that is going to be 0. So the sum of the forces equals 0. We're going to sum them up. Up is going to be our positive, and down is going to be our negative direction. We have Fn in the positive direction plus Fay is going to be equal to, then minus Fg is going to be equal to 0. So here's how we sum the forces up. Fn, the normal force, plus Fay, they both act in the positive direction. Minus or plus this force, which acts in the negative direction. So it's plus minus Fg, because Fg acts in the negative direction, equals 0. So now we're going to move Fay and Fg to the other side, and we get Fn is equal to, the normal force is equal to the weight of the object minus the component of the applied force that acts in the y direction. And that should make sense. The box has a weight. The weight does not change. But the force that is applied by the surface is reduced a little bit because part of the applied force acts in the y direction. It kind of takes up some of that normal force. Okay? It's not actually lifting it off the ground, okay, but it is taking up some of the force from the surface. We plug the values in, and we get the normal force is equal to 50 newtons, and we put that down like that. Okay, now the last thing we can calculate, and the last thing we need to calculate is the friction force. And the friction force, the equation for the friction force is mu, the coefficient of friction, times the normal force. Okay, we couldn't do this until we found the normal force. We actually had to find the normal force. Okay, so mu is 0.12, coefficient of friction times 50 newtons, and that tells us that the friction force is equal to 6 newtons. We'll write that in. Okay, so you can see we had to do a lot of calculating to find all those forces. There are really only 1, 2, 3 forces, but of course we had to break the applied force into its components. We had to find those separately. All right, now we can go on to the next page. Here I have the diagram without all those calculations, but we have all the forces there, and now we can calculate the acceleration of the object. We know it's moving in the x direction, so we have the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. That means that the acceleration in the x direction is equal to the sum of the forces in the x direction divided by the actual mass of the object. And the sum of the forces that are acting in the x direction are simply Fax and Ff. So it's 12.25 minus the normal force. Okay, 12.29 acts in the right, that's the positive direction. The friction force acts in the negative direction, subtracts some of that force, divided by the mass of the object, and the mass of the object's direction, and that tells us the acceleration in the x direction is 1.05 meters per second squared. Okay, so you can see, as I said, I think that problem seems a little easy at the beginning, but we had to do a lot of calculating, keep everything straight, and then we could find the acceleration. So I hope you found that helpful. If you did, you could leave me a thumbs up or a comment in the comment section below. Thank you very much for watching, and we will see you next time.